Welcome back to Chem 4300. In this video, we're going to finish up Chapter 4 on rotational motion. In this last bit, what we're going to do is derive the equations of motion for a rigid body. And we want to derive these equations from two different perspectives. One perspective is the space-fixed or inertial frame, looking up at an object. You can imagine looking up at the object and watching it rotate as it undergoes its motion. But the other perspective is from the point of view of the body. If we were fixed on the body in the principal axis system, we would want to look at its equations of motions. Now, to do that, we're going to have to first look at something called the rotating frame transformation. And then once we have that worked out, then we can look at something called Eulers' equations of motion for the rigid body. So first of all, if you think about that problem, trying to look at the equations of motion for a rigid body from the point of view of the principal axis system, you realize that there's a problem there. That's not an inertial frame. That's an accelerating frame or a rotating frame. So Newton's laws tells us that shouldn't work, right? But there is actually, in this particular case of a rotating frame, there's a correction we can do so that we can still continue to use Newton's laws. So this is what we're going to look at next, is what's called the rotating frame transformation. So imagine some vector q, some arbitrary vector, in an inertial space-fixed frame. So we would write out the vector as you might imagine with its components. And if we want to take the derivative of that vector with respect to time, if we want to know the rate of change of that vector in a space-fixed frame, then we would just take the derivative dq x dt times ex, dq y dt times ey, dq z dt times ez. And that would be fine. If we were thinking about this problem in the body fixed frame, this is the non-inertial rotating frame, then we would write the q vector in terms of the EA, EB, and EC with the components here. And then the rate of change in that frame would look like dqa dt times EA, dqb dt times EB, and dqc dt times EC, right? But what we'd like to know is, how is the rate of change in the space-fixed frame related to the rate of change in the rotating frame? These are two different time dependencies. What could look like it's not moving in the space-fixed frame will look like it's moving in a rotating frame, and vice versa. So let's look at how we can relate these two quantities, the rate of change in these two different frames. So let's go back to the vector written entirely in terms of the body fixed frame, but let's take the derivative with respect to the space fixed frame. So that means that we're going to still do dqa dt times EA, dqb dt times EB, and dqc dt times EC, which we recognize as just the derivative that we took in the rotating frame. But now, because this is in the space-fixed frame, remember in the space-fixed frame, the unit vectors along EA, EB, and EC, those unit vectors, will appear time-dependent. So that means we have to include QA times DEA dt, QB times EB dt, and then QC times DEC dt. So this time dependence of unit vectors is important when we're viewing the body fixed frame from the space fixed frame. So what we find then is that if we want to continue to describe these guys, we can just use the fact that the linear velocity of the unit vector, which it rotates about some given direction with an angular velocity, I'm going to use capital omega here for the rotating frame angular velocity, then that's going to be given by the cross product of capital omega with each of those unit vectors. So that means I can replace these derivatives with this expression here. So I'm going to take each of those derivatives, I'm going to replace them with the corresponding cross product, and I'm going to do a little rearranging. I'm going to move these components, Q, A, B, and C, over next to the unit vectors. And of course you recognize these unit vectors as just the total vector. So I can write down that that time derivative of this part of the expression is just going to be omega cross Q, which means I get back to my expression, which is that the rate of change of the vector in the space fixed frame is equal to the rate of change in the rotating non-inertial frame, plus we have to add in this extra term here to take into account the time dependence of the unit vectors. So this is how we're going to relate the change between the two frames. And this will allow us to continue to use Newton's laws as long as we add this extra term here in order to account for the frame change into a rotating frame. Okay, now we come to Euler's equations of motion. So we're going to describe, instead of Q now, we're going to describe the total angular momentum vector. And we know for in the body fixed frame, which is rotating about an angular frequency omega, that we can write dj dt in the space fixed frame is going to be equal to dj dt in the body fixed frame plus this added term. In the space fixed frame, we know the total angular momentum will not change unless there's an applied torque. And that relationship is given here, that dj dt is equal to the torque applied. So that means that we can just simply replace that expression here, this derivative with the torque, and this is Euler's equation of motion for the rigid body. So it's actually, once you get through the rotating frame transformation, it's a pretty simple derivation to get Euler's equations of motion. So let's take a look at this in more detail. This is a vector equation, so we'll look at its components here. So let's write down for the j vector, let's write it out in terms of the principal axis system, in the body fixed frame. And then we can take this vector equation and write down all the components of that, and this is what we get here with this definition. So this is the three coupled differential equations. You can see that the rate of change of omega a with respect to time is also in an equation where it depends on omega b and omega c, and similar with the other guys here. So we're going to look at a special case. We're just going to look at, in the rest of this chapter, the special case where the external torque is zero. So in other words, we have a rigid body that's freely rotating in space, no external torques applied onto it. And let's see what the Euler's equations of motion will tell us about those situations. So go back real quick. So you can see if these guys are all equal to zero, I can bring these guys over to the other side, and I can rewrite all those equations as these three coupled equations, like this. Now, what happens if there's not just no external torque on the system, but we also have the rigid body in space rotating about one of its principal axes? So it could be along A, B, or C. So if that was the case, then we would say, let's say we put it along omega C. So omega A and omega B are equal to zero. So if we're spinning along C, so that these guys are equal to zero, if A and B are equal to zero, then you see, well, up here, A and B are both equal to zero. That derivative has to be equal to zero, so the C component of the angular velocity vector is going to be time independent. But we also see there's an A here, that's equal to zero, so that means the B component's time independent. And you also see that there's a B there, that's equal to zero, so the B component, the A component is also time independent. So all three components are going to be time independent if there's no torque and the body is rotating about one of its principal axes. Okay. That's what we see from Euler's equation of motions. So we find that the angular velocity vector is not changing. So the rate of change of all three components is zero, so the magnitude and orientation of the omega, the angular velocity vector, remains constant in the body fixed frame, in the rigid body frame. And of course, since J is going to be equal to I C omega C, EC vector there, since that's the only component we have, then J is going to be independent. So J is going to have an orientation and magnitude that remains constant in the frame, and it's going to be aligned, we can see, with omega vector too. So it can be aligned with the angular velocity vector. So the angular momentum vector and the angular velocity vector will both be aligned and time independent in this case, where there's no torque and the body's rotating about a principal axis. Now, in the space fixed frame, we know, and generally we know, that J is conserved, right? So there should be no change in the total angular momentum viewed from the space fixed frame because there's no torque. So we know J has to remain constant in the space fixed frame before we even started any of this. But also we see now that J and omega are aligned in the body fixed frame and time independent, and that omega will also be aligned with J in the space fixed frame and time independent. Okay? So that was something we learned earlier in the class. If you see a body freely rotating about an axis and the axis is not changing, then it's spinning about one of its principal axes. Here is where that result comes from. Okay, now let's take a look at a different case. Let's say we have no external torque, but now the body is rotating about some arbitrary axis, an axis that's not one of the principal axes of the rigid body. Well, in that case, then all of these derivatives, if we're not spinning about any principal axis, all those derivatives are going to be non-zero. And as we look through this, we'll see then that all the components are going to have a time dependence that is, the derivative is not going to be zero, so omega is going to be time dependent in the body fixed frame. So if we're not spinning about one of the principal axes, then the angular velocity vector is going to be time dependent because all these derivatives are going to be non-zero. And since J is related to the angular velocity by J is equal to I dot omega, and I is independent, time independent in the body fixed frame, that means if omega is time dependent, then J is going to be time dependent in the body fixed frame. Okay? But we know in the space fixed frame, there's no torque acting on this system, so J has to be time independent. So J is not time dependent, or J is time dependent, J is time independent in the space fixed frame, but omega is not going to be time independent in the space fixed frame. And remember that I, when viewed from the space fixed frame, may not be a time dependent quantity. So that makes sense that J can be time independent, why omega is not. Okay, so now let's go on and look at a more concrete example of these equations. So let's take a look at this case of an oblate symmetric rigid body where this is the case where A and B are equal and C is unique, and that we're going to define C as I parallel and A and B as I perpendicular. And we're going to take the case where we're spinning about an arbitrary axis. So in that case, we expect omega to be time dependent, and we expect the angular velocity vector to be time dependent in the rigid body frame, but not time dependent in, of course, because this is free rotation, in the space fixed frame. So here are our equations, again, we're starting with. And so what we're going to do is we're going to take our conditions for the moment of inertia tensor, the principal components, and we define these values here. So what we see is that if A and B are equal, then this guy here is going to make the derivative of the C component equal to 0, whereas these guys are going to be given by these expressions here where I've substituted in the I parallel and I perpendicular. Now I'm also using Newton's dot notation for the time derivatives there. So what we're going to do is we're going to try to simplify our notation a bit. We're going to define a new angular frequency. This is a constant, which is, because C is a constant, it's not time changing, and these guys are all constant. So this is a constant number here. And we're going to define this quantity here as this capital omega naught. And if I do that, then these equations here come down to these very simple looking equations. Omega dot A is equal to capital omega naught times omega B, and omega dot B is equal to minus capital omega naught times omega A. So these are couple differential equations. This one depends upon B, and this one depends upon A. Okay, so they require knowing the solution of the other guy in order to solve it. So let's see how we're going to solve. This is probably the first time we see such an equation in this course. So let's look at how we're going to solve this pair of coupled differential equations. So in this case, there's one simple trick you can do to actually make this easy, and that is you just take the derivative again, the time derivative again of each of these. So if I take the time derivative again of this guy, this becomes omega A double dot is equal to capital omega naught times omega B dot, and over here it becomes omega B double dot is equal to minus omega naught, minus capital omega naught times omega A dot. Okay, so what did I gain by doing that? Well, I can go back to this expression for omega B and I can plug it into there, and I can go back to this expression for omega A dot and plug it into there, and when you do that, then you end up with two expressions that are second order differential equations, but now this one is entirely in terms of omega A, and that one is entirely in terms of omega b. So now we have two decoupled differential equations, which is what we wanted. So now we have to solve these equations. So we have some generic, actually both these equations have exactly the same form, so we can just solve one of them and we're going to have effectively the solution to the other. So we'll propose a solution of this form. So this is something you learn in differential equations. You just propose a solution and then you see if it works. And if it works, then you have a solution. If not, then you have to make another guess. But this is a good guess based on what we know about solving differential equations. And so we have these undetermined coefficients, a and k and b here, which will work out as we work through the solution. So we start out with our equation up there, and we're going to substitute this guy into these equations to see what we get. And I'm just going to do it in terms of the generic I instead of a, lowercase a and b here. And this is what we find if we substitute this equation into this one or this one. They all look the same. And you get this expression here. And what you see is that to make this guy equal to 0, there's one obvious solution. If we make capital omega naught equal to k, we're done. So if we set ki equal to omega naught, then we end up with these two solutions so far, right? So now this generic solution I'm going to write in terms of omega a and omega b looks like this. Now we still have these undetermined a and b for the a case and a and b for the b case, which we can work out by setting the initial conditions. So we're going to say that initially at time 0, the angular velocity vector is pointing along the a direction with a value of omega perpendicular and not along the b direction. So that means that this a and b here, this a becomes omega perpendicular and this b becomes 0. And over here for omega b, then initially it's 0, so that means that we're going to set a equal to 0 and here b equal to perpendicular, and then we get this result for the solution of our two components of their angular velocity vector. So we're solving the two equations, we get these two solutions. Okay, so let's bring it all together. That's just a and b. Let's bring it all together with omega c, which we know is constant. And okay, and so you can see right away that this solution is just an oscillation in the AB plane. So I forgot to mention that, but we'll see here now how this all comes together. So here we see the total length of the vector is going to be omega a squared plus omega b squared plus omega c squared, and then square root of all that. And if you go back to the previous result here, you see that omega a squared plus omega b squared, well, we're just going to have something that looks like cosine squared plus sine squared, which you see is going to go away, and that's going to be time independent. So that means that total omega is going to end up being time independent in this case. So the length of the angular velocity vector will stay constant. Now the angle that the angular velocity vector makes with the c direction is going to be given by this expression. So tan of the angle is omega perpendicular over omega c. And then with that definition, then we can just write this in this form here. So the angular velocity vector, which is time dependent, has the magnitude here given up by this expression. And then it's going to have, this is the component along the EA direction, which is going to be scaled by sine alpha. And then it's going to have this cosine omega t time dependence. And then on the B term is going to be scaled by, again, sine alpha. And it's going to have a sine time dependence with a little negative sign there. And then on the C component, it's just going to be scaled by cosine alpha. So that means that in this picture, we imagine this is the C direction. A and B are perpendicular to C. So that you can imagine then that this alpha vector is going to precess around the C direction with this sinusoidal oscillation on A and B as this system evolves in time. So this is what the time dependence of omega looks like in the body fixed frame. This is from solving the equations of motion. Next, we want to look at what happens to the angular momentum vector, which is going to be also time dependent in this case. So let's look here at what we know is that the angular momentum vector is just the dot product with the angular, with the moment of inertia tensor. So we can just go ahead and plug in our expression for omega with the moment of inertia tensor, and we're going to get this expression here. This is all calculated in the body fixed frame, the principal axis system. And so we get this expression here, which looks very similar, except we have some different scalings after we did that multiplication. So what we find now is that the j is the time dependent, and the angle that it makes from C is going to be tan theta, which we're going to define, and that's going to be JA over JC, which will work out to be equal to, tan theta will be equal to I perpendicular over parallel of tan alpha. So what we find then is that J is going to be at an angle theta, and it's also going to be precessing around the C direction in the AB plane, has a sinusoidal dependence in AB plane, and so we'll be precessing around the C direction like this in the picture. So there we have the picture for both the time evolution of omega and the time evolution for J. Now in this case, the oblate case, theta is smaller than alpha. If we switch to the prolate case, you'll see a switch where theta will be larger than alpha. Okay? And in this picture too, they have the right phase relationship so that EC, J, and omega are all in one plane as they move around in this time evolution. So that's it. We solved for the equations of motion for omega and J in the body fixed frame. Now in the space fixed frame, we do know that J has to be time independent, right? And so it's time dependent here in the body fixed frame, but in the space fixed frame, it should be time independent. So if we look at the difference between these two, in the body fixed frame, this is what we had. In the space fixed frame, the vector J has to be time independent. So that means that the EC vector, which is the unit vector along the C direction, is going to become time dependent in the space fixed frame. So J will remain constant. For this guy to remain constant, EC will start to precess around J. And again, omega will also then precess around J because that's the time independent quantity in the space fixed frame. All right, so that's it for chapter 4. And we've learned a lot about angular momentum and also rigid body motion.